Los Alamos, telling us about digital quantum simulations of TJ model in 1 and 2 dimensions on NISQ devices.
Thank you very much. Sorry for the hustle. I'm Amar Kirmani. I'm a postdoctoral researcher at Los Alamos National Labs. Today, I will be presenting our work on digital quantum simulation of TJ model in 1 and 2 dimensions on NISQ devices. So first of all, I really thank Lenel LDRD Grant and Center for Integrated Nanotechnology for their financial resources. I thank IBM Q Network and Quantinum for their quantum computing resources. Most of this work is done under collaboration with Jianqin Zhu, who is also my postdoc mentor. So let's get started. High temperature superconductivity was first discovered in 1986 in copper-based compounds usually called cuprates. A typical system is lanthanum-based copper oxide superconductor, where strontium, for example, strontium concentration X correspond to doping fraction. And as you change your doping fraction, your equilibrium phase diagram or phases are exotic, and your critical temperature may depend on your doping fraction. Highest critical temperature happens around optimal doping region of X equal to 0.15. So it's widely accepted that all these copper-based superconductor have copper and oxide planes, and most of your superconductivity or all of your superconductivity happens in those two-dimensional planes. Hence, we have a two-dimensional system that can be studied. It's also widely accepted that the symmetry of pairing is unconventional one or D-wave, and that's the reason for its high critical temperature. So if you want to solve this system with classical methods, and if you want to try with mean field treatments, you have strong correlations, so you will not go very far. Exact diagonalization is limited to small system size, maybe 10, 12 particles. Other approximate methods like density matrix renormalization group are limited to quasi-1D problems. So in equilibrium, these methods are not sufficient, while entanglement can further grow if you want to study out of equilibrium problem, and that's what we're going to discuss in this presentation. So here is our Hamiltonian for copper-based compound in all its glory. The first term is single particle hopping, and with hopping amplitude T. The second term is spin exchange interaction. So this model is derived from Hubbard model in strong U limit, where there is strong repulsion between on-site electrons. So here the Hilbert space is constrained in a way that if a site is occupied by a spin-up electron, it cannot be occupied by spin-down electron. So there can be at most one electron at each site. This is called half-filling constraint. And as you can see that this equation have half-filling constraint accommodated on-site fermionic operator. This is usually called Gauss-Willer constraint. So constraints usually help classical simulation because you remove some of this, some states from your Hilbert space. While for quantum simulations or for quantum computation, the situation is different. It may or may not help, as we shall see. So so the question that we are interested in a two-dimensional system, if we have a hole, what are the localization properties of the hole? Does it move, and how to know that the hole has moved from its place where it initially was? Since I have already said that classical methods are limited, we have to resort to quantum simulations. So let's see. So before we bang our head with a 2D problem, we first want to benchmark our result with 1D problem. That is, so our initial state has a hole localized at a certain site. So we have 1D system where hole was initially localized, and we time evolved that wave function by using Schrödinger equation. So what follows in this talk, we use tau for time and T for hopping amplitude. So yeah, this is a little bit constrained. So let's see what happens. So here we have our initial state where hole is localized in the center of a 1D system. And then, so I let it time evolve. Now it's kind of, it's not there, and now it's coming back there. Yeah, so it will come back now. Wholly. So hole is, these are dynamical property of holes. On the right side, we have time average density profile. So if electron density is low, it must be the position of hole, because absence of electron is a hole. So here we can see the hole is still localized, but somehow its localization has decreased. So qubits are spin, fermions are fermions. They have anti-commutation relation. We consult our old friends, Jordan and Wigner, and we perform Jordan-Wigner transformation. Based on what system you study and what kind of quantum device architecture you have, you may have certain polystrings that you have to deal with. So first question is, to take first step towards quantum computation, we want to know what is the complexity of such circuit. So please keep in mind that this has half-filling constraint in it. So we exponentialized this circuit. We found that our circuit is kind of a medium depth circuit. So we would like to study this or run this on different architectures. So for superconducting qubits, if you perform entangling operation between non-consecutive qubits, you will pick up overhead of extra operations, and then it degrades your performance. For trapped ion, you have all-to-all connectivity, so the situation is not as complicated because you have direct gates available between all systems. So even if we are studying one-dimensional problem, your circuit can demand more connectivity than your system can offer, although many of superconducting qubits architecture are like 1D. We can also simplify the circuit based on architecture, but that would be beyond the scope of this talk. So right now we benchmark with 3-side system. We localize hole in the middle of our 1D model. When we ran our circuit, what we realized that superconducting system, actually after 3 or 4 trauterization step, we did not recover proper. So this is initial position because your electron density is 0, that there was hole present, and after a certain time that hole was it came back to the same position. Our trapped ion device, which is Quantinuum model H11, did reproduce the result qualitatively. Some points are missing because it was expensive to run for the whole experiment. In conclusion, digital quantum computer can reproduce single hole dynamics of copper oxide, at least in 1D. Trapped ion system performance is much better for 1D. I think it's due to long coherence time. We are also studying 2D system for quantum advantage. The results are coming, but to see the results, you have to come to my talk next year. Thank you, and if I don't.